Okay, let's just dive right in. And look, I get it. This equation right here, at first glance, it probably looks a little intimidating, but I promise you, by the end of this, you're gonna see it not as a problem, but as a map. It's a map that can describe everything from the wobble in a bridge to the current in a circuit. We are going to break down a really powerful and honestly elegant strategy to solve these things and turn all this complexity into total clarity.
So here's our game plan. Think of this as our strategic battle plan. We'll start by decoding what the equation is even saying. Then I'll show you the core two-part solution strategy that unlocks everything. From there, we'll conquer each part, the complementary function and the particular integral, one by one. We'll watch it all come together in a live example. And then we'll wrap up with some key tips to make sure it all sticks.
All right, first things first. In any challenge, you gotta know what you're up against and what tools you have. So let's start by just decoding the language of these equations. At its heart, what even is a differential equation? Well, don't let the name scare you. It's simply an equation that has derivatives in it. That's it. We talk about their order, which is just a fancy word for the highest derivative you can find, and their degree, which is the power of that highest derivative. We're going to be focusing on linear equations, which are the absolute bedrock for modeling all sorts of real-world systems. Now, here is our secret weapon. This is our most powerful tool for this whole process, the operator D. Seriously, instead of writing out those long, clunky derivative notations, we just let the letter D stand in for d dx. So d squared is the second derivative, d cubed is the third, and so on. The magic here is that it transforms a really messy-looking equation into this beautiful, simple algebraic form, f of dy equals q. This one simplification is the key that unlocks everything else. Okay, so with our equation simplified, we can now reveal the core strategy. And this right here, this is the big aha moment. Every single solution to these equations is built from two very distinct, very logical parts. The total general solution, which we call y, is always, and I mean always, the sum of two pieces, the complementary function, or CF for short, and the particular integral, or PI. Think of it like this. The CF describes the system's own natural internal behavior, what it does when you just leave it alone. The PI, on the other hand, describes how that system responds to some outside force, which is our Q. So the total solution, it's just the natural behavior plus the forced response. So let's get to it. Part one of our plan. We're going to find that complementary function. To do this, we focus only on the left side of our equation, and we just pretend the right side is 0 for a minute. The process is a really slick three-step flow. First, we make a clever guess. We assume the solution probably looks something like y equals e to the power of mx. Now, when we plug this guess back into our equation, something kind of magical happens. The e to the mx term just factors out completely, and it leaves us with a simple polynomial in m. And that is what we call the all-important auxiliary equation. And once you've solved that auxiliary equation for its roots, for m, this table basically becomes your cheat sheet. The kind of roots you get, whether they're real and different, real and the same, or complex, tells you the exact form your complementary function takes. You just look up the case and write down the answer. It's a direct translation. All right, CFI is in the bag. Now it's time to tackle the second half of the problem, the particular integral. This is all about dealing with that function q that's been sitting over on the right side of the equation. To find the PI, we use what's called the inverse operator. It looks a little weird, that 1 over f of d, but all we're doing is algebraically rearranging the equation. Think of this operator as a specialized tool, almost like a targeted form of integration. Now, the specific trick we use depends entirely on what kind of function q is. Is it exponential? Is it trig? Is it a polynomial? Each one has its own special move. Case 1. If q is an exponential, like e to the ax, the rule is ridiculously simple. You just replace every single d in the operator with the constant a. But, and this is a big but, what if that makes the denominator 0? That's our failure case. But don't worry, the fix is easy too. You just multiply by x, take the derivative of the bottom part, and try again. For sines and cosines, the rule is just as specific. You replace every d squared with negative a squared. Now you gotta pay close attention here. It's not negative a the quantity squared. It's the negative of a squared. That little sign is a classic trip-up spot. And just like before, if you get a 0 in the denominator, you use the exact same failure case rule. And finally, what if q is a polynomial, like x squared or something? Here, our approach has to change. We have to wrangle our operator into the form of 1 plus or minus something, then bring it up to the numerator. From there, we use a tool you probably already know, the binomial theorem expansions, like the ones you see here, to turn the operator into a series of simple derivatives we can actually perform.
So we have all our tactics, we know how to find a CFF, we know how to find the PI. It's time for the final showdown. Let's apply this complete two-part strategy to a real problem and bring it all together.
Okay, let's walk through this. Look on the left, we find the complementary function. The auxiliary equation gives us complex roots, and according to our table, that leads directly to the CF with the e to the x and the trig terms. Easy enough. Now, on the right, we go after the particular integral. Here we use a special shift rule, since q is a product of two functions. We follow the steps, we simplify, and we arrive at our PI. And the grand finale? You just add them together for the complete general solution sitting right there at the bottom. And there we go. We've conquered the problem. Now let's do a quick post-battle debrief, just to reinforce what we've learned and make sure we don't fall into any common traps down the road. Here are 4 classic pitfalls to watch out for. First, those arbitrary constants C1 and C2, they only belong in the CF, nowhere else. Second, that sneaky sign error with the trig functions. I'm telling you, watch out for it. Third, always check for 0 denominators before you move forward. And finally, just be careful with your order of operations, especially when things get complicated. And here it is, your summary reference card. This one slide captures the entire logic of our strategy. On the left, you've got the 3 outcomes for your auxiliary equation roots. On the right, the specific rules for the particular integral based on what q looks like. This is your go-to guide. So, we've broken down the strategy, we've walked through an example, we've reviewed the key rules. That map we talked about at the beginning, it's yours now. So the only question left is, are you ready to test it out? Give these problems a shot, because mastering this isn't just about solving equations on a page, it's about learning to speak the language of how the world around us actually works.